All right. So yeah, okay. So we're talking about these two key algorithms to traverse the graph. Yes, the breadth-first search allows you to basically this is a foundation to find the shortest path from A to B, right? So if you just traverse layer by layer, then once you meet the destination, so say, suppose this is the south, right? So suppose you start from the starting point as,
Right.
and then you can pick any point as the end point.
Mm-hmm.
For example, here. So you go to the next level, nothing is E, and it goes to the next level, oh, this is E. Now you know that you are like two distance away from you, so you are minimum distance two. So
Right.
this algorithm is a foundation. So now how to implement this in code? Well, there is a very important data structure you used before, which is called, you know, um, there's a stack and there's a queue, right? So you're
Mm-hmm.
using a queue because you want to deal with, so what is queue, right? First in, first out, right?
Right.
So you want to deal with the this first level first before you deal with the next level. So you
Mm-hmm.
put the nodes into a queue one by one, and then you grab the first node from the queue. That's guaranteed to be from the root to the next level to next level, right? Because
Right.
you enter them in the order it was received.
Hence
So
why it's a queue. Okay.
that's why it's a queue.
Yeah.
Going to the code, I'm a visual person, so I like to illustrate it in the picture, but eventually I'll
Mm-hmm.
convert that to Python code, which is a text-based language. Let me go back to here. All right, so here you go. I have a queue. and now I use a dictionary to represent the nodes. And then the source is basically your study node. So
Mm-hmm.
you put the source first. If there's only one in the queue, that's the one. And then you keep getting it until your queue is empty. So there's multiple ways to express that. This is just one way. It's the length of queue is zero, that means empty. So if there's something in the queue, you do the following stuff. You pop left, well, this is the specific to Python language because the queue is the deck. You pop
Mm-hmm.
left, the left is the earliest node, right? That's your current.
Right.
And then you print them out because you traverse through I don't know what to do, just print out. And this is the key. For each node that's in the queue, it has neighbors. Now, graph algorithm, I skipped that before, is how you know. The key thing is how to represent the graph. And one of the three popular way is the neighbor, what do you call it? The nearest neighbor or the adjacency list. Okay, that's word. So the adjacency list is given this current node. It's a dictionary. Okay, so the dictionary has a key and value. The key is the current node. The value
Mm-hmm.
is all the node that's adjacent, the neighbor of the node. Okay, so you
Okay.
get all the neighbors from the current node. In the tree example, you have two nodes, but in the graph you may have many, right? So you iterate through that and you append that to the queue. And that's it. That's all you need to do. Because then you're guaranteed to go through your neighbors one by one. It may not necessarily in the order, in the same level, the order, doesn't matter because all you need to know is they are in the same level.
Right.
Mhm.
So when you're popping left, so like on the second row,
Yeah.
it's gonna pop the second circle or the one on the left first, right? And then the one on the right in
No,
this.
actually, the top left is always. So think about this. This is the queue. You take this structure, you put all
Right.
the nodes into a linear one.
Right. Into a dictionary. Yeah. So the top one would be
Oh, no, no,
index
no, sorry.
zero.
It's not in the dictionary. This is the queue. Queue is basically a linear array. You can think about that way,
Mm-hmm.
right? So you put the node in the linear array. It's just a different um, hotel to arrange those guests, right? Each node is a guest, and you
Mm-hmm.
put them into a room. with label 1, 2, 3, 4, and you let them go through the queue one by one. Oh, maybe you think about this way. You're going to an important party, and the queue is like a line before the door, and you are the doorman, and you want to check everybody's ticket, right?
Right.
So they're going one by one, but you want them to first come, first serve. So pop left is basically, hey, next person, next person.
Right. Mm-hmm.
Okay. The queue is a linear one. Now the graph, the dictionary is a different thing. The dictionary means each guest may bring some relatives or friends, right?
Right.
So you think about, say, if you Robert has Peter or whatever your friends, Mary, and they are your neighbors. So
Okay.
yeah, whenever I deal with you, I check your ticket and also check your neighbor's ticket and put all your neighbors in the queue. So they are
Right. Right. So we would all be like second in line.
yes.
Okay.
Now within your group, I don't care your order, right? As long as your group is the next batch to be processed, still one by one. This queue guarantees that you and your friends are dealt with first. Now your friends may have friends, okay?
Mm-hmm.
But that's secondary to you, right? Your degree of you heard about the movie what's it called, degree of separation? Like everybody in the earth, you can find your connection to Obama or any famous
Oh,
person
yeah, I see
by
what you're saying. Yeah.
3 or 4 distance, right?
Uh-huh.
And you can solve the degree separation use the graph algorithm too. And especially in this kind of fashion, right?
Mm-hmm.
So you will find that you put all the people on Earth into the gigantic graph because everybody has a friend circle, like your Facebook, right? You have friends. So that's exactly what Facebook is doing to search your friends. And I mean, like give you a link between you and other people.
Right.
Because he recommended you may be interested in connecting to other people. Why? Because your friends is friend with them. Okay. So yeah, this is a lot of applications. Very interesting. So, but yet this is very small piece of code, but it requires some thinking, right? But this queue is a key. It guarantees the order. So every time you go through this for loop and you finish with them, your level, let's see, yeah. Yeah, you finish this all for loop, you actually finish one level. You put all your neighbors into this,
Right.
and
And
then
then it's going to go
next,
back up and it's going to
yeah.
pop to the next person in line. And then it's going to see if they have any friends with them, so on and so forth.
So what you can do? Oh, this is this is different. I think I have a animation on here. Yeah, there's no animation, but yeah, you got the idea. Okay. So in
So
total, yeah, go ahead.
in the case of like the group of friends, would each row represent
Yeah, each level
uh,
represent.
friends, so to speak?
So this
So it
is
would be
you are
right,
top, and this is your 3 immediate friends, and your
right,
friends may have friends.
right.
So
Okay,
that's exactly, you can do this friend circle represented in this way.
right. Okay.
And then you want to say if this is Obama, and this is you, and you
Mm-hmm.
can say how far degree separation you from Obama, maybe 1, 2, 3, right?
Mm-hmm.
So that's how you calculate that.
Okay.
Yeah. Anyway, so and this is also a shortest path algorithm where if you can traverse and meet the end, and you just keep track of the level, that's the distance, right?
Mm-hmm.
So what you add in this code is to have a variable called level or distance. Every time you go through next neighbor, you add the level to +1, right? So you keep tracking of which level I'm in. It's not showed here in the queue, in this example, but it's easy to add a variable to keep track of levels, right? So then you can know, oh, how many degrees separation you're from some people. So I think the key for the graph problem is two things. One is, of course, you need to know this definition, but that's boring, right? Some edges and nodes. But that's a common language people are using, so you better get familiar with it. But after that, how to convert a problem into a graph problem? That's the key, right? Because you may not recognize this is a graphical problem to begin
Right.
with. So I think that the key is to give you lots of examples so you know, oh, this is a graph problem. Maze, maps, and then you can see, oh, which pattern it belongs to. Is this a, shortest path problem or
Right.
degree of freedom? And also how to represent the graph. So I'm going this not in order, but like we already, a JSON list is convenient because you can see in the code immediately you can know which my neighbor, right?
Right.
So this kind of dictionary now may not be dictionary, but dictionary is one way in Python that represent this. It's convenient.
So
Mhm.
in like the in the graph picture of like the map, so you can see that it has two different routes, right?
Mhm.
So, or actually it has three. So let's say the start is A and the end is C.
Right.
So you can go down, you want to go to that, you want to find like the quickest way, right? Is that pretty much essentially what's going on?
The shortest path. Now there's a lot of other things you can model like the traffic jam or whatever, right? But now let's just suppose there's no live traffic data, right? You
Mm-hmm.
you merely consider all these nodes by distance, okay?
Mm-hmm.
So so if you can just discretize, is there a word for that? The route, you know what I mean? And so you see all these points, you say, oh, this is the nodes, right? Going to A, B, C, D, F, G, dot Z, A to Z, let's say.
Right.
Starting from A equal to Z. And there's a lot of alphabet. And maybe A to B, A to C, A to D are the same distance.
Mm-hmm.
You don't know, but you want to try all of them. Okay. So the algorithm is that you try all of them.
So so for each, like for example, in the map picture, for each intersection, that would be a node. So like
Yeah, yeah, yeah,
you start at Harvard and then it looks like the next one would be like Worcester right there.
yeah, yeah.
So then that would be another one and then you can choose which way to go next, right? So that would be it leading down to the
Let me
next
let me
row.
show you. I think let me get a pic. I want to select a color that's okay. Red is good. So yeah, you start from Harvard. Draw. So this is our root. This is your starting point, right?
Mm-hmm.
And then the next is Rochester. Okay, so I draw this line. You
Right.
can see this is level one. So any
Mm-hmm.
point that is along the same distance with Rochester, maybe there's another one here. There's Rochester. There is another city. He will try all three, and then Rochester has the next level. Okay, so he will try this level, this level, this level. They are all on the same next route, and this one may
Right.
have next level, but they are all secondary, right?
Mm-hmm.
So you try them all in this. This is second level. And then
So
once this one has another level, and then you try that
right.
until layer by layer, until you hit yield. Okay.
Okay.
So, and then you may find 1, 2, 3, 4, the short distance is 5.
And that's just one case. Like we could be wanting to go to like Albany up there in the top left, and then that would obviously produce a different route.
Oh, yes, that's right.
Okay.
That's true. Yeah. So there's a lot of massive calculations in those that first search. You
Mm-hmm.
may end up with lack of computer powers. So there's a lot of technique to help reduce that calculation. That's why the map problem is complicated, right? So you can think about you can do double. So basically, you can also search from Yale to Harvard at the same time. Okay.
Mm-hmm.
And then when they meet in the middle, I mean, there is a tricky condition how you judge that, but that will shorten your search time by half because you're doing either both sides, right? But this is tricky, and that's just another way. But in reality, there is a lot of complicated decision. You may want to search A star search. A star algorithm is very popular for this kind of thing. Yeah, and I think the book may have some introduction on this. But then the basic idea is still the breadth first search. Now, of course, you can also assign some weight in the distance, right? So that's it makes it more complicated. Like I said, that the traffic information may be encoded into the weight. Although they have the same distance, if there's a traffic here, you get a higher weight there, so you don't go there, right? You pick the lowest weight first.
Mm-hmm.
So things like that, you can always represent. So I think the difficult part, how to model the real world situation into a mathematical model, right? Or computer model. So that's something that needs a lot of experience and practice, I think. Right? But I think the first thing is to familiar with the graph, and so you know there's something that you can use to do. Okay. But I know it's very hard, like adjacent matrix, another representation. So whenever there is a number, there's a connection, right, between V1 and V2 nodes. And then you can see oftentimes the graph is very sparse. This is sparse matrix. A lot of nodes have no connections. If that's the case, you're better off using adjacency list because that will save you space, but also will make your program more efficient.
Okay.
And oftentimes the problem is given to you not in the way that you like it to be. Like it will not directly give you adjacent list. It just give you A's connect to B, give you a list of connection. You need to translate that into adjacent list. I think I have an example in the slides as well. So I think we should go to the DFS, which is another important one, depth first search. This is very similar to the recursion idea we talked about earlier, right?
Yeah, except it's going through columns instead of rows.
So it's like in the tree, you go to the
Mm-hmm.
leftmost leaf first, and you keep going backward. This is the DFS is very popular too for a graph traversal. So one example, can you think of like what is best in using in depth first search? Like
Well,
search internet.
I would think the maybe the maze example.
The what race?
The maze, like
Oh,
up
maze.
top.
Yes, exactly. Right. So the maze you can just search to the end and back off if it's at that end, and the other way around. Now, of course, you can use breadth first search for the maze as well. Right? They both has pros and cons. Now, I'm talking about is if you have even in the level one, you have millions of nodes, right? That's the case when you search internet, right? It's almost impossible for you to finish it in time if you want to search something on the internet because there's tons of related messages, right?
Right.
Just for one level. So in this case, you may want to do a depth first search. That way, you may be able to find your document faster. But it's not guaranteed. It could still end up with a lot of going backwards and such, but at least you get one branch finished. If the depth is not that much, but the width is tremendous, right? So look at the shape of the graph, you can see which one is better. But again, depth first search is also using a similar idea. It's not using the queue anymore. Sorry, yeah, it's using a stack. Why a stack is like a first in, last out, right? So you're dealing with the last item first, last in, first out. So that's why you use a stack. So the idea is the same. You use a list to simulate the stack, and you keep pushing that neighbors, okay, into a stack. And then you just keep popping up the top of the stack, which is the latest one that you just visited, you just pushed, and then you deal with that way, the backward condition, okay? So oftentimes it is implemented in the recursion part, because naturally recursive function has a stack in it, right? Function has a function stack. So whenever you visit the next function recursively, you are pushing the current function into a stack, and you're gonna visit later. Okay. So that's why implicitly you don't see a stack when you're doing recursively, but if you do it iteratively, you do need a stack. Now, last we talk about the pros and cons of dealing with iterative versus recursion. In Python, recursion has a limit, right?
Right.
So this is how you do it iteratively, that we don't have that such a limitation anymore. So that's why. So you can see these are very similar instead of using a list, using a stack. So, okay, we're almost running out of time, but I want to just highlight that this is the two important algorithms that you need to practice on, and look at those examples. Yeah, so yeah, that's pretty much what I want to say.
Cool. Well, I don't really have any questions, so I just kind of wanted to get a little.
Yeah, I guess just give you an overview so you get some, when you're looking at particular things, you're not lost in the forest, right?
Right.
Okay, why this is, I'm studying this. I want to give you some incentives, but also a motivation, like which one is important, right? All else is important, but then the DFS and BFS are really important. And that is actually frequently tested in job interview. Right. So Google, if you go to Google, Amazon, Microsoft, these topics, are a favorite of job interviewer. So that's why. But of course, because they are important, right? So and it has tons of application, like Facebook problem and friend problem, all kinds of things, map problem. Okay, yeah. But Python, I think it has a very good language structure that you can code them very quickly. And I like the dictionary structure. Okay, sounds good.
Alrighty, awesome. Thank you for your time today.
Yeah, and next week is still the graph, so bye.
Alrighty, bye.